Our planet is a world of constant transformation. The ground beneath our feet feels solid and permanent. Yet, the surface of the Earth is anything but static. It is a dynamic canvas, perpetually reshaped by powerful forces. Over vast stretches of time, mountains rise and then wear away. Oceans open and close. Rivers carve deep canyons through solid rock. Glaciers grind entire valleys into new forms. This ceaseless activity creates the incredible diversity of landscapes we see around us. To the deepest ocean trenches, every feature tells a story of creation and destruction. Understanding these processes is the key to reading the epic story of our world. The scientific discipline dedicated to this story is geomorphology. It is the study of landforms, their origins, their evolution, and the processes that sculpt them. Geomorphologists act as planetary detectives, piecing together clues from rock formations, from soil layers, and from the very shape of the land. They seek to understand why a mountain range exists in one place and a vast, flat plain in another. They investigate the forces that build landscapes up and those that tear them down. This field bridges geology, geography, and physics, showing the Earth as a complex, interconnected system. Imagine soaring high above the Earth. Below you, the planet's surface unfolds like a magnificent, textured map. You see the towering, jagged spine of a young mountain range. You glide over expansive, ancient plateaus. Great rivers appear as silver ribbons. Immense sheets of ice and monumental glaciers flow slowly but relentlessly. Along the continent's edges, you witness the endless battle between land and sea. These landscapes are not random. They are the visible results of a great planetary drama that has been playing out for billions of years. The forces at work operate on scales that are difficult for us to comprehend. Some events, like an earthquake or a volcanic eruption, happen in seconds, unleashing incredible energy. Other processes, like the slow grinding of a continent or the gradual weathering of a granite boulder, unfold over millions of years. To truly grasp the story of our planet's surface, we must learn to think across these immense timescales and appreciate both the sudden cataclysm and the patient, incremental change that shape our world. The multitude of processes that shape our planet's surface can be divided into two fundamental categories. First are the endogenetic forces, which originate from within the Earth. Driven by the immense heat stored in our planet's core and mantle, these forces are the primary builders of relief. They thrust rock upwards to form vast mountain chains. These internal forces manifest as tectonic plate movements, earthquakes, volcanic activity, creating the initial rugged framework upon which all other processes act. In constant opposition to these constructive forces are the exogenetic forces. These forces originate from outside the Earth, or more accurately, on its surface. They are powered primarily by energy from the sun. Solar energy drives the climate system, creating wind, rain, snow, ice. These elements act as powerful agents of change. They relentlessly attack the landforms created by internal forces, a process known as denudation. Exogenetic forces work to wear down, break apart, and transport rock and soil. They strive to level the landscape, smoothing out the rough topography and carrying the debris to lower elevations, eventually depositing it in basins and oceans. We will begin by journeying deep into the Earth to understand the engine that drives endogenetic processes. We will explore the theory of plate tectonics, witnessing how the slow dance of continents generates earthquakes, fuels volcanoes, and builds the world's greatest mountain ranges. We will examine the specific landforms created by this internal power, from deep rift valleys to towering volcanic cones. We will provide clear, step-by-step explanations for complex phenomena like folding and faulting, using real-world examples to illustrate their impact on the landscape we see today. Each concept will be presented with a slow, deliberate pace to ensure clarity. Then we will turn our attention to the surface, to the exogenetic forces that sculpt and refine the land. We will investigate the slow, subtle work of weathering, which breaks down the toughest rocks. We will follow the powerful agents of erosion, water, ice and wind, as they carve, transport and deposit material, creating a stunning variety of landforms like canyons, U-shaped valleys and vast dune fields. Finally, we will see how these two great architects, the internal and the external, interact in a continuous and dynamic struggle. This interplay, governed by climate and unfolding over geological time, is what makes the Earth a living, constantly evolving planet. To comprehend the immense power of endogenetic forces, we must first journey deep into the Earth, far below the surface we inhabit. Our planet's interior is a place of unimaginable heat and pressure. At its center lies a solid iron core surrounded by a liquid outer core, both generating a powerful magnetic field. Above this lies the mantle, a vast layer of semi-molten rock or magma that constitutes the bulk of the Earth's volume. This internal heat is the primary engine driving all endogenetic processes. It is the furnace that forges continents and fuels the volcanoes that have shaped our world for eons, a relentless source of energy that continuously works to reshape the planet from within. This tremendous internal heat originates from two primary sources. The first is residual heat, a leftover from the planet's violent formation some 4.6 billion years ago. During its accretion, the gravitational collapse of dust and gas, and the constant bombardment by asteroids and comets generated an enormous amount of thermal energy, much of which remains trapped deep within the Earth. The second, and more significant source, is the continuous radioactive decay of unstable isotopes, uranium, thorium, potassium. This slow, steady release of energy acts like a planetary-scale nuclear reactor, constantly replenishing the heat that drives geological activity and keeps our planet's interior dynamic. This heat does not remain static. It is constantly in motion, seeking to escape towards the cooler surface. The primary mechanism for this heat transfer within the mantle is convection. Hotter, less dense material from deep within the mantle slowly rises, while cooler, denser material from near the surface sinks back down. This process creates massive, slow-moving, circular flows known as convection cells. The energy generated by this internal engine is not released uniformly across the globe. Instead, it is concentrated along specific zones, primarily at the boundaries of the lithospheric plates. It is here that the true power of endogenetic forces is unleashed upon the surface. The constant slow-motion churning of the mantle builds up immense stress within the brittle crust. When this stress is suddenly released, the ground shakes violently in an earthquake. Where the convection currents rise, magma can breach the surface, resulting in volcanic eruptions. And where these currents push the plates together, the crust buckles and fractures, thrusting rock upwards to create the planet's most magnificent mountain ranges. The modern understanding of how these internal forces shape the Earth is elegantly explained by the theory of plate tectonics. This theory, which revolutionized the Earth sciences in the mid-20th century, posits that the Earth's lithosphere is not a single continuous shell. Instead, it is broken into numerous large and small rigid segments called tectonic plates. Continental crust, oceanic crust. These plates are in constant, slow motion, floating atop the ductile asthenosphere beneath them. They move at speeds of a few centimeters per year, roughly the same rate at which our fingernails grow, driven by the underlying mantle convection currents. This seemingly slow dance is the primary driver of most major geological events. The interactions between these moving plates occur at their boundaries, which are the most geologically active regions on Earth. There are three main types of plate boundaries, each defined by the relative motion of the plates involved. In the most recent chapter of Earth's long story, a new and powerful geomorphic agent has emerged: humanity. Through our collective activities, we have begun to alter landscapes and modify surface processes at a rate that rivals, and in some cases exceeds, natural forces. Widespread deforestation agriculture removes the protective cover of vegetation, exposing soil to accelerated erosion by wind and by water, leading to land degradation and increased sediment loads in rivers. The construction of dams dramatically alters a river's flow and sediment transport, trapping material in reservoirs and starving deltas of the sediment they need to survive, causing them to sink and erode. As our journey through the 18-minute story of Earth's surface concludes, we are left with a profound sense of dynamic change. Our planet is not a finished piece of art, but a living, breathing system in a constant state of becoming. It is shaped by the fiery heat rising from its core and sculpted by the sun-driven forces of its surface. The landscapes we cherish are merely a fleeting moment in this grand, continuous saga. The only constant is change itself. As we stand on the surface of this restless world, we are participants in its story, privileged to witness a snapshot of its magnificent evolution.